Okay, so we just started our discussion of Simondon's individuation in the light of notions of form and information. We're still on part 1, chapter 3, I believe, if I'm not mistaken, and then we're reading section 2. The passage we're on is starting on page 122 of the translation, and we're looking at the inductive method that leads to the corpuscular theory of light. That's just a summary of what we did before the recording started.
So could I just ask, so when you're saying discontinuity, is this in the sense of being countable units then, like you said, so discontinuity in the sense that, they're restricted beings, quote unquote, with that are different from one another?
The discontinuity here is that the amount of charge needed to release hydrogen from water, for example, you can't get like a half of that charge or a quarter or whatever. So the charge only comes in these units of like if you set 1 to be the amount needed to cause the hydrogen to be released, then you find only multiples of that 1 unit. So 1, 2, 3, etc. times that unit, rather than having any fractions of that charge unit. Whereas if we started with an idea that electricity was something continuous, that it was like a stream of some continuous energy or something like that, then we would expect that you could have a continuous variation in electrical quantities, so that you could pass from 0 to 1 continuously. Whereas what we find instead in these types of experiments is that you can only have integer multiples of this unit charge. So the role of the depositing here it has to do with the type of experimental setup that's in question. So you have basically a solution inside some sort of container, and then you have a negative end where the current is produced, and then you have the positive end, and so the hydrogen will separate from the water and then be deposited on the cathode, if I'm not mistaken. So the negative end, right? And then the same thing when you have other substances like silver or whatever, they'll be deposited on one side of the experiment. So yeah, it's the deposition is just where the result sort of ends up, or where you can observe the result. So hydrogen or silver or whatever separated out from the solution in which it was before.
Should we continue reading? And if so, do you mind if I do that?
Yeah, go ahead. So from the top of 123.
This initial inductive discovery was followed by a second discovery that reveals the same method and ends in the same result. After 1895, which is the date of the discovery of X-rays, it will be shown that these rays can make gases conductive by creating a conductibility identical to electrolytic conductibility, in which electrical charges are transported by ions, this time not based on the decomposition of a molecule, but on that of the atoms themselves, since these ions exist even in a monoatomic gas like argon or neon. This decomposition allows for induction to progress one step further in the research of structures. Stoney's electron remained a quantity of electricity associated with an indivisible physical particle. It now becomes more substantial because the ionization of gases requires a structural representation in which the negative electrical charge is freed from this heavy support of the electrolytic ion. Ultimately, the discovery of structures was able to reach a new stage 2 years later. If we are restricted to measuring quantities of electricity that pass through a column of ionized gas, we can conceive the independence of the electron with respect to any heavy material particle. But this independence remains abstract. The experimental principle is what allows us to safeguard the phenomenon. If, on the contrary, we push the experimental research further by attempting to physically analyze the content of the discharge tube when the pressure of the gas reduces, we obtain the Crookes dark space that pervades the whole tube when the pressure falls to 1/100th of a millimeter of mercury. This space, which develops very progressively from the cathode while pressure decreases, in some sense makes palpable the physical analysis of the initially continuous ensemble that was the ionized gas, in which free electrons could not be discerned from the other electrical charges, namely the positive charges carried by the ions. At that point, we were able to suppose that the Crookes dark space contained free electrons in transit. The experiments on cathodic rays were considered experiments on free electrons. It could certainly be said that in this latter experiment, the discontinuity of electrons disappears at the same time as their association with a phenomenon, such as the ionization of a liquid or a gas in which they appear as charges of a determinate magnitude associated with the particles. All the experiments conducted at this time on cathodic rays were macrophysical and revealed the existence of electrical charges in transit in the tube without indicating a discontinuous microphysical structure. The experiment cannot be carried out on a single electron. The luminescence of the glass tube, the perpendicularity of the rays with respect to the cathode, their rectilinear propagation, their chemical and caloric effects, the fact that they transfer negative electric charges, and their deviation under the influence of an electrical and magnetic field are just a few of the macrophysical effects with a continuous appearance. However, due to the inductive path at the end of which this discovery was obtained, it was necessary to suppose that these cathodic rays were composed of discontinuous particles of electricity, because in this way the structure of the experiment was taken into account. The electrons of ionized yet still undifferentiated gas in the disruptive discharge, according to the experiment structure, are identical to those occupying the Crookes dark space. The latter are identical to the electrons of which the cathodic rays consist. The electrons of the ionization of a gas at the moment of disruptive or non-disruptive discharge are identical to those transmitted by the negative ions in the electrolysis of a body.
Yeah, so some of this is a little bit obscure because it's some early electrical experimentation. So the Crooks Tube was developed in 1860 something, I believe, and was used up until like the end of the 19th century. So it's the way a Crooks Tube works basically is it's a glass bulb, like a light bulb, and then there's an electrical current introduced at one end, the cathode end, and then you have an anode at the other end, so a positive charge at the other end. It's a little bit complicated, but the sort of basic principle is that it produces a stream of electrons that flow from the negative end to the positive end. It actually flows, the electrons flow past the anode and hit the glass wall behind the anode and cause it to glow, which you can see in the chat there. There's the little picture preview from from Wikipedia. So that's what a Crooks tube does, and the second stage here, the point of introducing this Crooks tube example is so when you have this, the first stage here is the discovery of X-rays and the conductibility of gases. After the discovery of X-rays in 1895, there's this discovery that by shining an X-ray through a gas, you can create this conductibility in the gas, so that in the same way that in the electrolytic experiment, you had the electrical current produce the conductibility in the solution. In the same way, you end up when you shine the X-ray through the gas, you have this conductibility in the gas. This happens not only when you have, so it's not just molecular bonds that are being broken in this experiment, but even when you have a monoatomic gas, so a gas that's composed of one of single atoms, like argon and whatever the other one was, I forget. Neon, right? So argon and neon are monoatomic gases. They're composed of single atoms, and you still, when you spray them or illuminate them with an X-ray, you still end up with this ionization process. So the electrons are being freed from the atoms themselves and not just from the molecular bonds. And so this was the sort of the first demonstration of a subatomic particle. So whereas in the electrolytic experiments, you could still understand these unit charges as being associated with some sort of heavy particle, like a piece of matter that would have a mass and everything. Now in this X-ray experiment, you have the unit charge is liberated from being tied up with an atom or something like that. So it gives us the depiction of electrical charge as having its own sort of corpuscular reality. It's something independent of the atoms in which it normally occurs. The next bit has to do with right in the Crooks tube. So you have the Crooks tube. It works with very low pressure of gas within the tube. It's not quite a vacuum, but it's a low pressure of gas. So it has the one end that lights up in when the electrical current is applied, and then the other end has the positive charge, which is carried by ions of the gas, whatever gas is in the tube. And you can actually, he mentioned this a little bit later on, but you can actually have a cathode with little holes pierced in it, and that allows the ions produced in the gas to flow in the opposite direction towards the cathode. And then the other end of the Crookes tube will light up as well. So you have one end that lights up because the electrons are hitting the wall. That's the anode end. And then the other end, the cathode end, will light up because the ions are hitting the other wall. So both sides can light up in that version of the experiment. But in this experiment, in this version of you have these cathodic rays, so rays of what are considered free electrons, so electrons that are not associated with an atom. And then you can determine the properties of these rays. So things like the fact that they heat up a substance that they hit. So if you have a piece of metal inside the chamber, it will heat up the metal or whatever it is. The fact that electric or magnetic fields will deviate, will cause the stream of electrons to deviate. So normally it will be in a straight line. The stream of electrons is in a straight line perpendicular to the surface of the cathode. But then in the presence of an electrical or a magnetic field, the stream will be deviated by that field. So you can look at all these different properties of the stream of electrons. But what Simondon points out in that second part of the paragraph is that all of these properties are just as you can account for them just as well under the assumption that electricity, these cathodic rays, are being produced in a continuous manner. So you don't need the assumption of discontinuity or of the corpuscular nature of electricity to account for the straight line nature of the ray or any of the other things. Yeah, I'm riding the transductive wave. Right. What was my last point? Oh yes, and so the presumption of discontinuity here comes from the fact that you have the electrons are supposed to, according to this account of the process in the Crookes tubes, the electrons are supposed to be released from the gas in the chamber in the bulb. So if we assume that before the release of the electrons, they have this corpuscular form, then we have to also assume that once we introduce the electrical charge and then produce this stream of electrons, they must also still have this corpuscular form. So it's a sort of an argument from homogeneity, I guess. It's the idea that there's the same nature of electricity is at work whether the electrons are bound in the gas or free in the stream. So that's sort of the mode of reasoning for that experiment.
Should I read the next paragraph? Can we consider the inductive method followed in these three interpretations of the experiment as transductive? It is not identical to what appears in the formation of the notion of waves. Indeed, the notion of waves was developed to allow for the introduction of a deductive thought into an increasingly broad domain through the expansion of the object. It corresponds to a primacy of theoretical representation. It allows for the synthesis of several results that were separate beforehand. On the contrary, the notion of corpuscles of electricity was introduced to allow for the representation of an experimentally observed phenomenon by means of an intelligible structure. At the start, it does not surpass the numerically formulable law, but gives it a representative substructure through which an intelligible schema can be paired with the phenomenon. When we move from one experiment to the other, for example, from electrolysis to the ionization of monoatomic gas, we transfer the same schema. We discover a new case for the application of the previously discovered schema. But the case is only new experimentally and not due to an extension of the object. The electron is always the same, and it is because the electron is the same that induction is possible. On the contrary, when the continuity between visible light and Hertzian waves is established, it cannot be said that light is made of Hertzian waves. Instead, we define the limit that separates and joins these two bands of the domain of transductivity we explore. Should I read the next paragraph?
Yeah, sure. Go ahead.
Okay. The thought that led from Faraday's laws to the calculation of the mass and charge of the electron carried out a transfer of identity. The thought that led from the laws of electricity and from Fresnel's formulas to Maxwell's electromagnetic theory carried out the development of a domain that opens up into a continuous infinity of values. Now we are able to distinguish much more clearly in Maxwell's effort between what was merely deductive from what was really transductive. Maxwell did deductive work when he wrote the formula of the displacement current in order to be able to account for the conservation of electricity and join together in a single system of equations the four laws that summarize the whole science of electrical phenomena. But he needed a veritable transduction when he joined the theory of displacement currents with that of the wave propagation of light. The necessity of the continuous is a direct consequence of the application of the deductive method. Yet, since a deductive invention is necessary for a transductive progression to be realized, we in fact have in the examination of the birth of wave theory a mixture of the deductive method and the transductive method, rather than an absolutely pure example of the transductive method. Likewise, it is possible to find several traces of the transductive method in the development of the notion of electrified corpuscles. The discovery of rays formed by negative corpuscles of electricity has also led to the search for rays formed by positive particles or positively charged materials. Positively charged material particles. With a cathodic ray tube that has a cathode pierced with holes, we have obtained not positive electrons, but positive rays formed by ions originating from the gas contained in the tube. This is what forms the basis of the study of isotopes with Aston's mass spectrograph. This research leads to a veritable discovery of a vast domain of transductivity when, remarkably, the interpretation of isotropy managed to confirm and complete the periodic classification of elements established by Mendeleev in 1869. The classification itself was the result of a vast induction formed on the consideration of atomic weights and the result of an effort of transductivity oriented toward the periodicity of the properties of known elements ranked by an order of increasing atomic weights. We should note that there is a difference between a domain of transductivity obtained at the end of an essentially deductive process and a domain of transductivity obtained at the end of an essentially inductive process. The first is open on both ends. It is composed of a continuous spectrum of various classified and organized values. The second, on the contrary, is self-enclosed, and its scope has a periodic structure. It comprises a finite number of values.
Right. So here we have some, I guess, specification of these three modes of thinking and the relation between them. So we have the deductive, inductive, and transductive, and they're all sort of tied up with each other. So he sort of goes back to the last subsection and the discussion of the deductive method, and now he wants to distinguish between what is properly deductive in the development of the wave theory of light, and then what is properly transductive in that development. And so he sets out. So he says that writing the formula of the current of displacement of the displacement current for to capture the conservation of energy is a purely deductive operation. So there's one aspect of that development that Maxwell does that is purely deductive. But then there's a transductive moment of that process when Maxwell relates these displacement currents to the theory of light, to the propagation of light in wave form. It's this moment where the mode of thinking passes from one domain to another and opens up this new domain of electromagnetic radiation. That's the transductive moment in that first strand in the wave theory of light. And then likewise within the corpuscular theory of light and its development, you can find these moments of transductive method as well. So that right, it's the passage from the negative rays, so the cathode rays, to the search for a positive ray, so the anodic rays or the streams of positively charged ions separating out from the gas. And so again, we have the transfer of a schema of thought from one domain to another domain, and that's what is the properly transductive moment. And then he goes on to introduce this new set of facts having to do with the way that. So I don't know this part as well, but in as far as I gather, it's the way that you can use the anodic rays, so the rays of positively charged ions. You can use that to study the nature of a particular substance. So it's you can if you take an unknown substance and create these anodic rays with it, you can determine what the nature of that substance is based on the pattern.
Yeah, I think I agree with Aldreams here that while a lot of the experimental discussion is way over my head, it's really interesting how he's setting out the difference between these different methods. And I was reading I think everyone should definitely read it, his little tidbit on allegmatics, which I think is at the end of one of these books, that was compiled from his notes. But it's just another sort of attack or approach to him talking about the theory of operations and what is the theory of operations. And ironically, it really fits these last few sections because it seemed like the intuitive transductive sort of origins of this whole philosophy for him, because in it's sort of like notes towards an investigation, and he's saying, oh, use Fresnel's examples and use Maxwell, so he sort of has these inklings that these things indicate and demonstrate these forms of thinking. But I just like how, I guess what I'm trying to extract from this the best that I can is there's a bit in that allegmatics piece where he's talking about, he's again going back to the idea of analogy and how analogical thought establishes a relation between two terms. but it's only able to do that because thought itself is its own kind of mediation between an operation and a structure in the being who's thinking in the first place. So thought is sort of, we've been talking about individual milieu a lot, but he kind of talks about thought as that milieu in that essay that is able to create the relation between these different things that are being discussed, and he even criticizes, we can go into another time, what he calls Bergsonian intuition in that essay, but his point is, for it not to be a metaphor, thought itself, as we're saying, it has to have a real transductive sort of capability, and making thought a kind of ground, or I think maybe he says elsewhere, a topology of the real rather than something that is separate from it, which I know that sounds it sounds like I'm plugging in terms, Simonian terms here, but I have a feeling it does somewhat make sense.
Yeah, he's stated a number of times that we've seen so far, the way that thought has to be understood as a process of individuation, so that we know individuation by individuating in our knowledge, undergoing a process of individuation in our knowledge. And so, so because of that, we have to understand the thinking subject as part of a larger system that is undergoing individuation, rather than as a sort of abstract, self-contained substance, which then has to have some sort of external relation with the object known. I just wanted to finish on the periodic table, because I think this is an important example for him. So the way that Mendeleev develops the periodic table is just by the atomic number atomic weights of the different substances, and he sort of discovers this periodic structure of these atomic weights, so that you find that substances, elements that have these different properties, or that have similar properties, recur at regular intervals if you arrange the elements in order of atomic weight. And so he sort of comes across this periodic structure of the elements, but he doesn't have he doesn't have an account of what the basis of that periodicity is. And so you can regard this as sort of just an external classification of substances. It's just something that helps us to organize our knowledge of elements, or something like that. But what this the Aston mass spectrograph, what it does is gives you an independent confirmation of the periodic structure of the elements. So you have an alternate means of accessing the pattern of elements, and you find that these two independent means line up with each other. So that confirms this periodic table structure of the elements. And it's only in the 20th century that some of the basis for the periodic structure is made clear through subatomic physics. So yeah, that's the sort of the role of this the periodicity, and he states, so he makes a distinction between the domain of transduction that appears at the end of the deductive process, and the domain of transductivity that appears at the end of an inductive process. And so the electromagnetic spectrum is characteristic of the domain that appears at the end of a deductive process. So it's an open-ended domain, so it's open at both ends. You can have electromagnetic radiation of any wavelength, and there's no maximum or minimum. And then on the contrary, the domain of transductivity that appears at the end of an inductive process is closed and has this periodic structure. It has a finite set of values that can appear. So there's this difference of structure of these domains depending on which mode of thinking it comes from. Okay, so that's the end of that section. So we're going to go on to section 3. And if you thought the physics stuff in the last section was hard, then you'll be in for a treat in this section, because we're going to be talking about relativity first, and then quantum mechanics, and in particular about this alternate interpretation of quantum mechanics known as the double solution theory. So we'll go into that more when we get there. But the first bit is about relativity and how it relates to the notion of individuation. So I'll read the first couple paragraphs here. So section 3, the non-substantial individual, information and compatibility. Subsection 1, relativistic conception and the notion of physical individuation. One of the most difficult problems of reflexive thought is the problem of the relation that can be established between these two results of transductivity. If transductivity conducted based on deduction led to the same results as one conducted based on induction, reflection could be reduced to a search for the compatibility between these two types of results, which are acknowledged as legitimately homogeneous. If, on the contrary, a hiatus remains between these two types of results, reflection faces this hiatus as a problem, for it is neither possible to classify it in a continuous transductivity, nor localize it in a periodic transductivity. The invention of a reflexive transductivity will then be necessary. The fourth stage of inductive research relative to the corpuscle of negative electricity presents the same characteristic as the previous three, but in a certain sense it introduces the elementary quantity of electricity in the individual state, not in its visible corpuscular reality, but through the discontinuous effect that it produces when it is combined with a very fine material particle. Here still, we see the discontinuity of electricity manifested by a situation where variations of the charge of material particles are produced. The electron is not grasped directly in itself as an individualized particle. Millikan's experiment, in fact, consists in introducing between the plateaus of a condenser very tiny drops of a non-volatile liquid, oil, mercury. These drops are electrified by their passage into the atomizer that produces them. In the absence of a field between the condenser's electrodes, they fall slowly. When a field exists, the movement will accelerate or slow down, and the variation of speed can be measured. Yet by ionizing the air included between the plateaus, we observe that the speed of a given drop undergoes abrupt variations from one moment to the next. These variations are interpreted by admitting that the charge of the drop varies when it encounters one of the gas's ions. The measurements show that the captured charges are simple multiples of an elementary charge, equivalent to 4.802 by 10 to the minus 10 electrostatic units. This experiment is complemented by those in which the electron intervenes through the discontinuity of its charge. Let us nevertheless note that this discovery of the corpuscular nature of electricity allows a mystery to remain: the dissymmetry between positive electricity and negative electricity, which cannot by any means be predicted inductively in the corpuscular theory. Positive electricity would never be present in the free state, whereas negative electricity is present in the free state. Indeed, there is no structural reason for a corpuscle to be positive or negative. A qualification of the corpuscle cannot be easily conceived. Quality appears in the different modes of the possible combinations of elementary corpuscles, but it cannot be easily conceived at the level of this simple structural element that the corpuscle is. Here we come up against one of the limits of inductive thought. Its need for simple representative structures leads it to consider quality as something irrational. Quality resists inductive identification. However, since the 18th century, experimentation has indicated the qualitative differences of vitreous electricity and resinous electricity. In order to reduce the element of irrationality, it would be necessary to be able to transform the specific qualitative difference into a clear structural difference. But also, since induction tends toward the simple element, it also tends toward the identification of all the elements with respect to one another. After the discovery of the fact that negative electricity is a universal constituent of matter, we have been able to believe that all matter is made of electricity. In this sense, induction through identification would have consummated science. Chemistry and physics would have become a generalized electronics. But reduction to absolute identity had been impossible because it could not remove the dissymmetry between two forms or species of electricity. It has indeed been possible to consider that a charge of positive electricity is nothing but a hole of potential created by the departure of an electron. But on the other hand, we then are surpassing the limits of induction, seeking the simple structural element, And on the other hand, we are supposing the reality of a material support made of a substance other than negative electricity. For if all matter were constituted by negative electricity, the departure of an electron could never create a hole of potential that would manifest as a positive charge equal in absolute value to the electron, but with a contrary sign. The veritable limit of induction is plurality in its simplest and most difficult form to cross, heterogeneity. It is starting from the moment when inductive thought is faced with this heterogeneity that it must resort to transductive thought. But when it encounters the results of deductive thought, whose limits it also finds at a certain point. Inductive thought is found lacking when a representation of the pure discontinuous is insufficient. Deductive thought is found lacking when a representation of the pure continuous is also found lacking. This is why neither of these two modes of thought can lead to a complete representation of the physical individual. The physical individual then has recourse to the invention of different systems of compatibility for the methods or the results. But such epistemological conditions involve a necessary critique of knowledge fated to determine which degree of reality can be apprehended through the invention of a system of compatibility. Right, and Angus has posted in the chat some description and an image of the Millikan experiment, so that's very helpful. Thank you. And yeah, so that's my understanding as well. The sort of value of this experiment is that it allowed to measure the charge of a single electron, so that you give a greater reality to the notion of an electron as a free, as an independent unit of electric charge, but also as a physical particle, which is capable of existing in a free state. And then the next bit here is sort of the obstacle at which this inductive thinking reaches when we come to think about the difference between positive and negative electricity. So we any sort of the basic principle of corpuscular thinking, or the strategy of corpuscular thinking, is to always reduce any qualitative difference to some sort of arrangement of corpuscles. So the corpuscles themselves would not have any sort of intrinsic qualities, but the combination of these corpuscles in a certain manner would produce qualities that we can observe at the macrophysical level. That's the sort of general strategy of corpuscular thinking. And the problem or the obstacle that you run into is that the distinction between positive and negative electricity is this qualitative distinction that remains at the microscopic level, so that it's not really possible to sort of reduce the qualitative distinction to some sort of arrangement of corpuscles, because your corpuscles of electricity, your electrons, are already characterized by this qualitative distinction of positive versus negative electricity. And so we have this attempt to identify matter with electricity so that everything would be made up of electrical charges, but this heterogeneity of the two forms of electricity, positive and negative, sort of resists that reduction. And then one possible or one attempt to get around this difficulty is to say that positive electricity would really, or what is called positive electricity, would really just be a hole of potential. So it's the absence of a negative electricity. This Simondon argues that this account doesn't really work, because if everything was just made up of negative electricity, then there would be nothing for that hole of potential to subsist in. That representation of a hole of potential implies some sort of support in which the charges inhere. And so we're stuck with this obstacle where inductive thought runs into its limit, and then as we saw earlier, the deductive thinking also runs into its own limit, and so that we need a mode of thinking that can unify or pass beyond the distinction between the discontinuous and the continuous. And this is precisely Simondon's thought of the individual. And so he will specify a little bit later on that any true relation, so relation understood as having the status of being, a relation is always between a continuous term and a discontinuous term, so that there's unification of the continuous and the discontinuous in relation, and this underlies the separation between the continuous and the discontinuous. Yeah, there's that passage a little bit earlier where Simondon separates his method from the dialectical method as he understands it, and he argues that the synthesis or the result of transduction is in some sense horizontal. It's not something superior to the terms united in the way that in the dialectical process the dialectical synthesis is ontologically superior to the terms that it joins. That doesn't mean that there isn't something like a synthesis. So I'd have to go back to that specific passage. But he says something like the synthesized, it never is never completed. The synthesis is never completed in his mode of thinking, in the transductive mode of thinking. But it incorporates the asymmetrical within itself. So it incorporates the continuous term and the discontinuous term within itself, but without sort of going to a higher level in the way that the dialectic is supposed to do.
Yeah, that makes sense to me. The only thing I was saying is that you can kind of fall into this linguistic trap. What I don't think that's necessarily what you were doing, but when you're saying synthesis, kind of, because you could look at it and be like, okay, allegmatics, and again, I'm sorry, I'm just thinking about this because I was reading that essay where he's saying like, so allegmatics is the study essentially of individuation, of the individual, but it doesn't. But you could mistake that for then being like, well, if transduction is sort of like the superior method, then therefore the individual is sort of like the higher or preferred term. But as we know from all this reading, like the individual it's almost, to the way I can see it, is like it's the point at which you can genealogically enter into peeling back all these layers. And so the individual, in that essay, he talks about it as, he even defines the individual as being a kind, like he uses the word internal tension, incompatibility. It's before he uses the word supersaturation, which is what he always uses in the crystallizations conversation. So it's interesting of like, I'm only bringing it up, I'm hoping not to confuse things, but in the sense of, we should think of it as, in that essay as well, he's talking about analogical and analytical science, and he's trying to say that even though it's kind of clear that Simondon falls closer to what I've always been arguing, that Bergsonian kind of intuition, he's critiquing even that model for, as we just read, anything that purely prioritizes operation over structure, or the reverse. It's like you don't get to transduction because you could do an operational kind of reading that is focused exclusively on relation, that almost becomes a kind of like postmodernism that would be maybe, I think, a crude and mistaken reading of what Simondon is trying to do. And it seems like he's trying to say you can't, just because there are flaws with the deductive kind of reasoning at a certain limit and with inductive reasoning at another limit, it's not like these just go out the window. Like as you say, you can start from an inductive or a deductive thought and arrive at transduction, but they don't, nothing cancels each other out. And in fact, that like the milieu and the relation is about, like you said, it's horizontal and it's holding all of the elements together, and you can kind of shift from one to the other to perceive it in a new light, or maybe as you advance along that kind of like transductive process. And again, I don't think I don't know if I'm arguing against what you were saying. It was just sort of in my head as I'm trying to piece it together. I just thought unifying might sound a little bit kind of like too much like the kind of philosophy he's criticizing.
Yeah, that's a helpful reminder. I think he does use the term unifying in other contexts, but it might be safer to avoid that term for this specific operation of thought that he's talking about here. In the sort of bigger picture, what he's talking about in this whole chapter has to do with the complementarity, the complementarity of the wave and particle depictions of light in particular. What he wants to argue is that this complementarity is a result of sort of applying the conceptual thinking to something that is not thinkable through concepts in the proper sense, or in the sort of restricted sense that he wants to give to the term. And so the individual or individuation can't be understood through concepts or conceptual thinking. It has to be understood through what he sometimes calls intuition. But this is not something sort of mysterious and distinct from scientific research, because he thinks we can have a science of the individual, or we can produce knowledge of the individual through science. But it has to do with the mode of thinking, the way that these representations are connected to each other, rather than some sort of like supernatural faculty of intuition or something like that. But yeah, so just all that to say that what he wants to do is to show how this complementarity is a result of sort of a one-sided approach to the individuation process, and each of the complementary concepts grasps a part of the reality of the individual, but only one part. And that's why you have to think of light sometimes as a wave, sometimes as a particle, or and the same thing with electrons. Will have a wave aspect and a particular or corpuscular aspect. But let's go on to the next bit from the top of 128, if someone else would like to read.
We find this beginning of a discovery of compatibility between the inductive method and the deductive method, between the representation of the continuous and that of the discontinuous, in the introduction of relativist mechanics into the domain of the free electron. Other means of producing free electrons have been discovered. And I just want to note that I think that's the point of this paragraph, is that these are just other ways of producing free electrons. The Cathodic Rays accompanied by the so-called thermionic effect, and then the beta decay of radioactive bodies. It was known how to determine the trajectories of electrons in space by noting their points of impact on fluorescent screens or photographic plates capable of being affected by this impact. Wilson's cloud chamber, of which it has been said that it constituted the most beautiful experiment of the century, made it possible to follow the trajectory of an electrified particle. At the end of the studies carried out by Perrin, Viard, and Lenard, the electron could be represented as a corpuscle, i.e., a very small object that can be localized in space and that obeys the laws of dynamics of the material point. In an electrical field, the electron, which has a negative charge, is submitted to an electrical force. In a magnetic field, when it is in movement, the electron behaves as a small element of a conduction current and is submitted to an electrodynamic type of Laplace force, simultaneously perpendicular to the direction of the magnetic field and to the instantaneous direction of movement. And it is numerically equal to the vectoral product of the electron speed through the magnetic field multiplied by the charge. Under the action of this force, F equals E over C V times H, the electron's movement occurs like the movement of a material point with a mass of 0.9 times 10 to the negative 29th grams. Rowland's experiment in 1876 established that displacement of electrical charges produces a magnetic field, as if it were a question of a conduction current produced by a generator and a fixed conductor. The inductive value of this discontinuous conception of electricity was particularly revealing in the sense that it made it possible to bring the study of the movement of electrons back to the mechanics of the material point, a theory which has been considered classical for quite a while.
I think we can go on to the next bit, which is where relativity comes in.
Okay. Yeah,
Page or so.
I can keep reading a little bit. The new mechanics remained theoretical when it was applied to bodies studied by macrophysics. Relativist mechanics is indeed valid for all material bodies. It had already successfully explained the three phenomena in 10 to the negative 8 that classical mechanics had failed to explain. The theory of relativity gained a lot of momentum when it explained the perihelion of the planet Mercury, which had been noted much earlier. The deviation of sunlight observed during an eclipse confirmed the principle of special relativity. Color changes from moving sources of light led to the same confirmation. However, this theory of relativity, which is the mechanics of extremely rapid movements, could still be contested in the domains of macrophysics. Speaking about the theory of relativity, Le Chatelier declared in his work L'industrie, la science et l'organisation au XXe siècle, quote, similar speculations can interest the philosopher but shouldn't captivate men of action who claim to shape nature and guide its transformations, unquote. Further on, he adds, quote, today the probability of seeing the laws of motion and Lavoisier disproved is not even 1 in a billion. It is therefore madness to be preoccupied with similar eventualities or to speak of them and be distracted by them for one instant, unquote. Le Chatelier focused his argumentation on the fact that relativist theory only gives results different from those of classical mechanics for bodies animated by speeds above 10,000 kilometers per second. Quote, however, on Earth, we do not know how to produce speeds above 1 kilometer per second, which is the speed of the projectiles of the famous Big Bertha, which is a howitzer cannon, apparently. There is hardly anything save the planet Mercury that possesses sufficient speed to warrant relativistic speculations. Even in this case, the predicted perturbations are so weak that we are still not in agreement of their magnitude, unquote. Should we stop there? Or...
Sure, yeah, we can stop there.
I looked up the perihelion of Mercury thing. So apparently this has to do with the precession of the orbit of Mercury around the sun. And Mercury has an eccentric orbit, which I guess means that the orbit itself changes. It's more elliptical, I think, than the orbit of other planets, and it changes more frequently. But the classical Newtonian explanation for the way it changes leaves a certain degree of its actual change unexplained, and that is explained somehow by relativity when you take into account the potential well around the sun itself, which slows down the orbit of the planet as it gets closer to the sun.
Basically, there's a slight inaccuracy, or there's a slight deviation between the predicted orbit of Mercury under Newtonian physics and the observed orbit of Mercury. There's a slight deviation, and Einstein predicted that that you would be able to observe that, he explained this deviation through the fact that in relativistic physics you have this inverse relationship between speed and mass, so that well, sorry, how to explain this? So in the presence of a large mass like the sun, you have differences in the way that space-time is structured. You have a well of potential, as Angus posted in the chat. So you have basically a stretching of space-time in the vicinity of this large mass, and that means that the the orbit of Mercury is slightly different than what Newtonian physics would predict, and it's accounted for by relativistic physics. And so that image in the chat there shows the deviation. Apparently, physics is too spicy for our server here, so we'll have to look for it somewhere else. But yeah, that's sort of the big picture of what this perihelion of Mercury was, and this was considered at the time one of the most important confirmations of the relativistic physics. And yeah, so but as Simondon cites this Le Chatelier, who says that all this is basically nonsense. It doesn't really matter, and we shouldn't sort of concern ourselves with all these speeds that are so much greater than anything we can produce. I like a book for 12 wise men. Right, and then another confirmation of the theory of relativity was the deviation of light in around an eclipse, which is in that clip that Angus posted. So there's basically the idea is that the ray of light coming from a star near the sun in our visible sphere. So the apparent location of the star is near the sun. So normally you wouldn't be able to see it, but then when there's an eclipse, you can see this star near the sun. And what you find is that the location, the apparent location of the star is slightly different from where it should be. So that, and this is explained by the light beam traveling from the star to Earth is deviated by the gravity of the sun. And this was another prediction by Einstein. And so when this observation was made in the early 20th century, it was considered a strong confirmation of relativistic physics.
I was listening to some podcast about this kind of thing, and they were talking about a relatively recent experiment where, just similar to the solar eclipse experiment, where they observed a supernova explosion behind a galaxy, and it actually, like, the lens effect created 4 copies of the same supernova explosion, I think for the same reason, which is interesting.
Right, yeah, there's like more complicated versions of the same type of effect through gravitational lensing. So the gravity of the sun, or in this case of a galaxy, would be sort of having the same effect as a lens on a ray of light. So it causes it to deviate, and it can produce double images, or I didn't even know about quadruple images. But yeah, that's one of the effects that Einstein predicted would be a way of confirming relativistic physics, and that disconfirmed Newtonian physics, and so that's why it was considered like a sort of decisive experiment at the time. And yeah, so we have to sort of, this is one of the these long paragraphs that Simondon loves, or these long developments where we don't see the sort of the point of what he's introducing until you read a page or two into the development. But he's going to argue that within relativistic physics, there's a sort of it sort of decenters the sort of corpuscular theory. Yeah, we'll get to that in a little bit, but the idea is that within relativistic physics, you don't have the idea of a corpuscle as a sort of self-contained substance in the way that you did in classical physics. Yeah, and so this is well, 1905 is sort of the birth of both relativistic physics and quantum mechanics in a couple of different Einstein papers, but relativistic physics is sort of developed and widely accepted much more quickly, and then quantum physics takes more time to develop and to be accepted. Yeah, it's not for men of action. Yeah, that's a nice quote. It's always nice to see people like from 100 years ago or whatever just being completely wrong about things. It sort of helps helps like put things in perspective. And just in terms of like as an aside here, just in terms of the practical use of relativity, like satellite TV or anything involving satellites is only possible because of relativistic physics. It's only like if you tried to calculate the motion of satellites and where the signals would end up and so on, based on Newtonian physics, you would end up with the wrong predictions. So that's a completely practical use of relativistic physics that, of course, Le Chatelier couldn't have known about, but it's not just like at the realm of speculation or something like that. Okay, so let's go on to the next bit. I think we stopped at we're at the second argument on page 129, if someone else would like to read.
The second argument is that, concerning the transformation of radium into helium, all the scientists that have worked on this problem still have not managed to produce altogether 10 milligrams of this gas. However, considering the millions of tons of material that the industry transforms every day, an exception to Lavoisier's law has never been able to be verified. From a macroscopic and pragmatic point of view, Le Chatelier was perhaps correct. He could seemingly accuse the partisans of relativity of corrupting through their skepticism regarding Newton's law of gravitation and Lavoisier's law of the conservation of elements, the students who were overly inclined to follow the snobs and philosophers declaring that these two fundamental laws of science are nothing but the vestiges of an obsolete past, just as Aristophanes already accused Socrates of a word that I can't read. If someone wants to get that for them. What is that?
It's kainologia.
There you go. In the clouds, facing the Athenian public who were anxious about the spread of new ideas. Nevertheless, both on earth and in simple assemblages made possible with the physical apparatuses of an established instruction at the time when Le Chatelier rose up against the negation of all good sense for dotting the I's and clear explanation, there were already bodies animated by speeds above 10,000 kilometers per second, namely electrons in transit in cathodic ray tubes. These corpuscles belonging to microphysics due to their dimension, but in a tube that is several dozen centimeters long and with the energy that can be accumulated at the limits of the secondary winding of a Ruhmkorff coil, it is possible to transmit to them a speed above that of the fastest celestial bodies. Here there is a discovery of magnitudes that in the usual classification of phenomena were not of the same species. A corpuscle 1,836 times lighter than the hydrogen atom behaves like a planet during an experiment that is on the order of magnitude of a human body and that requires a force comparable to the force of our muscle. The mechanics of relativity profoundly modifies the notion of the individual existence of a physical particle. The electron cannot be conceived like an atom was formerly conceived because it rapidly changes place. Ever since the ancient atomists, the atom was a substantial being. The quantity of matter that it constituted was fixed. Mass invariance was an aspect of this substantial invariance of the atom. The atom is the corpuscle that is not modified by the relation in which it is engaged. The compound results entirely from the atoms that constitute it, but these first elements, The primordia rerum are not modified by the compound that they constitute. The relation remains fragile and precarious. It has no power over the terms. It results from the terms which are not modes of the relation in any way.
Yeah, we can stop there. So this is what I was mentioning earlier when he's going to argue that relativistic physics modifies the notion of the individual because in relativistic physics, mass is relative to speed, for one thing. So as we'll see in the next paragraph, the mass of a corpuscle or of a body in general increases as speed approaches the speed of light. So this is completely different from the conception of mass as a fixed quantity of a substantial element or a substantial atom. So that in classical atomism and even up until the end of the 19th century, the idea is that the atom is a self-contained substance, and it undergoes these external relations, but those relations don't change its being. Whereas in relativistic physics, the relation between entities, so like the speed, changes what the mass of those entities is.
Could you help explain that last sentence, or this last paragraph where you're saying the relation remains fragile and precarious, it has no power over the terms, it results from the terms, which are not modes of the relation in any way. I know he's talking about the atomistic sort of conception there, but in a very accidental way, and I think because I'm just not understanding the terms, that sounds quite similar to the way he talks about the importance in transduction of having the independence of the operation from the terms, in analogy at least. And so but here I'm just trying to not confuse them. Here, is it different because he's saying the relation has no power over the terms and it results from them, and so it's not it's not a milieu in the way that he later or earlier has talked about things.
So I think the difference is so on the atomistic conception, relations are purely external to entities, to the terms related. So you have atoms that have their own particular properties, like mass and whatever other properties that an atom has, and those properties don't change. They're inherent to those atoms, and the atoms then secondarily undergo these relationships that are purely external and form compounds. And the compound bodies are fragile and precarious, as he says, because they're always secondary to the atoms themselves. So the compound can always be dissolved. And then the atoms sort of return to their free state. Whereas in Simondon's conception, relation in the true sense is constitutive of the being of the terms related, so that it's always relation has the status of being, as he puts it, so that there's always an internal aspect to relation. So you can't isolate a substantial term from the relation in which it inheres. And then the question, Al Dreams, you had about the relationship between relativistic physics and the wave-particle duality. Yeah, so they're not directly tied to each other. So you can, like, for example, you can, and actually this is a sort of an open problem in physics, is how you relate quantum physics with relativity. They're sort of two separate domains that are each successful in their own sphere, but then how you tie them together is not really clear at the moment. Yeah, so we remain agog, like in the clipping. And yeah, so string theory and other approaches to unification have been proposed, but nothing has been sort of considered to be successful so far. One of the issues is the ability to perform some of these experiments. We're sort of like running into limits in terms of the energy needed to perform some of these experiments. That would be able to differentiate between different accounts of the relationship between quantum physics and relativistic. Yeah, there's a number of different approaches which are sort of like head-hurtingly complicated, and I don't know a lot about that area of physics. But yeah, it's definitely an open problem how to connect relativity and quantum mechanics. Okay, so let's go on to the next couple paragraphs. With the electron envisioned by the theory of relativity, the mass of the corpuscle is variable according to speed, formulated by Lorentz's law as m equals m0 over square root of 1 minus v squared over c squared, where m0 is the mass of the electron at rest, i.e. 0.9 by 10 to the minus 27 grams, and c is the speed of light in vacuum, and v the speed of the corpuscle under consideration. The dynamics of relativity therefore presents us with a corpuscle which cannot be characterized by a rigorously fixed mass representing the substantiality of an unchangeable matter, a support unmodified by accidental relations, but which also cannot even receive an upper limit for a possible increase of mass and consequently for the energy conveyed and the transformations able to be produced in other bodies by this particle. The whole set of principles of atomistic thought that seeks to get the inductive clarity of corpuscular structures is put into question by Lorentz's law. Indeed, from the point of view in which we are situated to consider each particle in itself, it has already produced a profound change, since the fundamental characteristics, like mass and the quantity of transported energy, must be conceived as not having an upper limit. Mass tends toward infinity when the speed v tends towards the limit c, which measures the speed of light in vacuum. The individual no longer has this essential characteristic of the atom of the ancients, which is that of being strictly limited by its dimension, its mass, and its form, and which is consequently endowed with a rigorous identity through time, an identity that makes it eternal. But the theoretical consequence of this change in the conception of the physical individual is truly even more important if the mutual relation between particles is considered. If, under certain conditions, a particle can acquire an energy that tends toward infinity, there is no longer a limit to the possible action of particle on another particle or a group of other particles, however large that group may be. The discontinuity of particles no longer imposes the finite characteristic of possible modifications. The smallest element of a totality can receive as much energy as all the other parts combined. The essentially egalitarian nature of atomism cannot be conserved. The very relation of part to whole is transformed, because the relation of part to part is completely modified from the moment that one part can exert on the other parts an action stronger than all the other elements of the whole taken together. Since each physical individual is potentially unlimited, no individual at any moment can be conceived as safe from the possible action of another individual. This mutual isolation of atoms, which for ancient atomists was a guarantee of substantiality, cannot be considered absolute. The vacuum, an invaluable condition of energetic isolation and structural independence, which was for Lucretius the very guarantee and condition of the individuality of atoms and their eternity, can no longer ensure this function, because distance is only a condition of independence if action through contact alone is effective. In this substantialistic atomism, shock can modify the state of an atom's movement or rest, but not its own characteristics like mass. However, if mass varies with speed, a shock can modify the mass of a particle by modifying its speed. The accidental, totally fortuitous encounter affects substance. Passivity and activity are merely two symmetrical aspects of energy exchanges. The actual or potential passivity of substance is as essential as its potential or actual activity. Becoming is integrated into being. Relation, which contains the energy exchange between two particles, includes the possibility of a veritable exchange of being. Relation has the value of being because it is allegmatic. If the operation remained distinct from the structure that would be its unmodifiable support, the substantialism of the particle could attempt to account for energy exchanges by a modification of the mutual rapport of particles, thus leaving the respective characteristics of each particle unmodified. But since every modification of the relation of one particle to the others is also a modification of its internal characteristics, there is no substantial interiority of the particle. Here still, the veritable physical individual, as in the case of the crystal, is not concentric with a limit of interiority that constitutes the substantial domain of the individual, but is on the very limit of the being. This limit is actual or potential relation. An immediate belief in the interiority of beings qua individual no doubt comes from the intuition of the body proper, which seems, in the situation of a man reflecting, to be separated from the world by a material sheath that offers a certain consistency and delimits a closed domain. I'll finish this paragraph. In reality, a suitably deep psychobiological analysis would reveal that the relation to the external milieu for a living being is not merely spread out on the external surface of itself. Through the mediation that it constitutes between the exterior milieu and the being, the notion of interior milieu, which was formulated by Claude Bernard for the necessities of biological investigation, indicates on its own that the substantiality of the being cannot be confused with its interiority, even in the case of the biological individual. The conception of a physical interiority of the elementary particle manifests a subtle and tenacious biologism that was apparent even in the most theoretically rigorous mechanism of the ancient atomists. With the appearance of the theory of relativity on the plane of the current physical experiment, this biologism gives way to a more rigorously physical conception of individuation. Let us note, however, that if the possibility for an increase in the mass of a corpuscle had a limit, we could return to a substantialistic atomism simply modified by a logical dynamism. Leibniz's monad is still essentially an atom because its stages of development and involution are regulated by a rigorous internal determinism of the concrete individual notion. It doesn't matter that the monad possesses within itself a recapitulation of the modifications of the monads of the whole universe as a microcosm in the form of little perceptions. In fact, from the point of view of the causality of modifications, the monad only draws its modifications from itself and remains absolutely isolated in becoming. The limits of its successive determinations are rigorously fixed by the system of universal compossibility. On the contrary, the physical individual, which is thought according to relativity, has no limits of its own defined once and for all due to its essence. It is unbounded. Because of this, the physical individual cannot be determined by a principle of individuation comparable to what Leibnizian dynamics assigns to it. The limit, and consequently the relation of the individual, is never a boundary. It belongs to being itself. Yeah, there's a lot in this one long paragraph. So the first bit here is, so in this equation, you can see that as V approaches C, then the whole equation approaches m0 over 1. The part underneath the square root approaches 1 minus 1, so it approaches 0, and then so as it approaches 0, it can never actually reach 0, but as it approaches 0, that means that the total mass can increase without limit, so that what this shows, according to Simondon, is that the particle can't be understood as something substantial and self-contained anymore. So even when we're just talking about a single particle, it doesn't have these inherent properties like mass anymore. Its mass, it depends on its speed. And then even further, when you introduce more than one particle, you find that through the interaction of one particle with another, one particle can change the mass of the other particle by changing its speed. So what looks like an external relationship or purely accidental contingent part of the history of a particle can change what would seem to be its inherent properties, like its mass.
Yeah, I'm going to need to reread this section before next week because it feels so, like, I mean, he obviously establishes it by the end, but even when he's still talking about the, relativity proper, it's like he's already starting to set up these axioms of this discontinuity of particles doesn't impose the finite characteristic of possible modifications. The smallest element of a totality can receive as much energy as all the other parts combined. Like, I really like that he's bringing this back to, I guess, just what we started the book with. And yeah, just as we were saying, that all the stuff we were talking about earlier with the Kleineman and the early atomists, it's coming back, and just the statement there where he says passivity and activity are just two symmetrical aspects of energy exchanges. I don't have an interesting thought here. I just love that it feels like the science and the philosophy aspects are really coming together in this section.
Yeah, I think Angus posted in the chat about how this section really shows how contemporary science or 20th century science really makes it impossible to hold on to the traditional atomistic picture, which with modifications was sort of the default position of most scientists up until the end of the 19th century. The idea of atoms as these self-contained substances, and then everything else being made up of these atoms. So we see here that relativity, to start with, will make that harder to maintain, and then even further when we get to the quantum mechanics stuff, it becomes even harder to maintain that picture.
I think the application to Leibniz is really interesting. It seems like what he's saying is that the lack of an upper limit for the mass of a particle. We could see Leibniz's monads as being, in a way, extremely large because they perceive the entire compossible universe in the form of these little perceptions, but they're limited by the idea of compossibility and incompossibility. So, not even like Epicurean atomism, but even Leibniz's kind of strange version of atomism is impossible, or it is inconsistent with contemporary science. And interestingly, I think that compossibility and incompossibility are parts of Leibniz's system that Deleuze rejects.
Yeah, I think the Leibniz bit. So the reason why Simondon thinks that the lack of limit to the energy that a corpuscle can have, or to the mass that a corpuscle can have. On Leibniz's picture, each monad contains within itself the sort of self-regulation of the entire universe, right? So each monad is like a clock set up independently of all the others. They don't have windows, as he says. So there's no real effect of one monad on another, but the internal evolution of the monad is set up in such a way that it sort of replicates the rest of the universe, and what looks like causation of one monad onto another one, it's really just the internal evolution of both of those monads in the synchronized manner. So what this absence of a limit of the mass shows, according to Simondon, is that you can't there can't be anything like this internal principle governing the evolution of a monad, because it would still be limited. So the evolution of the monad would have to be limited in some way, whereas the mass and energy of a particle are unlimited as speed approaches the speed of light. And so you can't have something like this sort of internal governance by the principle of the individual concept of the monad.
I've noticed too that there's the whole. I love this bit about the limit when he's saying if you take that notion of the limit when it comes to like biological being, and it kind of commonsensically, you can look at an idea of interiority in like the body of the person who is doing observation and all that. But he brings it back again at the end where he's saying the limit is not a boundary; it belongs to the being itself. So it kind of, I think it brings us back to just again the very start of the book and thinking about the limit as a productive point that continues to generate further becomings and further individuations. So there's never actually a hard sort of line between inside and outside, or interiority and exteriority. Like interiorities and exteriorities are something that are produced in the process of an individuation, and they're like one of the phases. So when he talks about, again in the other essay I'm thinking about, where he's talking about, you have to think of the individual as a state, as one of the possible states. In the primordial so-called state, or in the pre-state, there isn't a division between interiority and exteriority. But once there becomes one, or a potentially observable one, it doesn't mean that is sort of, that's all there is. That interiority and exteriority itself is produced, and that there could still be future sort of developments afterwards. And at least in the crystal example, that with the idea of the end part of where the crystal develops can develop further crystals, but then even in the the modulator examples with the tubes and the electricity, which obviously I'm less I understand less, but when he was talking about the continuous modifications that the modulator is able to do, I feel like these are sort of the elements he's bringing back with trying to reintroduce the idea of the limit not as something that's actually a limit, but is part of being, and therefore part of becoming.
Yeah, I think the bit about the interiority is interesting, because this is another instance of Simondon trying to sort of retrace the steps of a mode of thinking back to this sort of fundamental image or primordial image that it's drawing from, and so he argues that atomism is drawing from the experience of one's own body as something like an envelope around an interiority, and then he argues, this is just sort of an aside at this point because we're still talking about physical individuation, but then he brings up this concept that Claude Bernard had introduced of the interior milieu, so that within a living individual, there's something like a milieu, so that you can't just sort of draw a boundary around the living individual and say everything inside this boundary is interior, and then everything outside the boundary is exterior, because even within the boundary there's already a sort of interior exteriority, if that makes sense. So that even in the case of the biological individual or the living individual, you can't just sort of hold on to this substantialism about the interiority. So the sort of lived experience of being an individual with a body and having this boundary around yourself, that experience is misleading when we sort of try to apply it to the notion of an atom that would have this interiority in the same way. So I think we're about at time. So we'll pick up from halfway down 132, or I guess close to the bottom of 132 next time. So thank you everyone for showing up, for your questions and comments and everything. And see you all next week.